This is Daniel Cousberry, and we are going to continue looking at some probability theory. I just finished a series of videos that introduced us to some basic probability concepts, and now I think we're ready to build on those to some ideas that give a lot of shape and structure to finding probability. These next few videos are going to focus on what are called random variables, and this whole video is just going to introduce us to what that means. And like I said, random variables are nice because they're going to give us some structure to some more kind of interesting probability problems and give us some rules that'll help us work through things. So let's start by defining a random variable. So random variable is a numerical outcome of a probability experiment, and I went ahead and wrote down an experiment here that's familiar to us. We're going to roll a six-sided die and record the outcome. And we know with a six-sided die, there's 6 different outcomes, 1 through 6. And we can describe this as a random variable and represent it in a table like this. So usually with random variables, we give each variable a name with a capital letter. I'm going to call this capital X. So the random variable X is, I'm going to roll a six-sided die one time and write down the outcome. These are the 6 outcomes it can get. And then the probability of X for each of these outcomes is given by 1/6. So if it's a fair die, the chance it lands on any of these is going to be 1/6. So it's really nice. So this is one way to represent a random variable. But in general, random variable is an outcome of a probability experiment. So we can define different kinds of experiments as random variables like this one. Just like with data, we had, with numerical data, we had discrete data sets and we had continuous data sets. We have the same for random variables. Discrete random variables are random variables whose possible values can be listed. So they're like the counting numbers or something where you can, if it's possible to list them all, then you've got something discrete. Like for instance, the number that comes up on a die or the number of siblings a randomly chosen person has. So oftentimes with discrete, we're counting things like 0, 1, 2, 3, 4, 5 or something like that. Continuous random variables, you can't count the possible outcomes. Instead, you're going to use an interval. So with continuous, we're thinking of intervals like a range of values. I tend to relate this to a ruler. So like there's a range of values between any 2 marks, and you can't list all those possible values. It's just impossible. There's decimals and fractions involved, which is why we use intervals instead of instead of listing them all. So for instance, the height of a randomly chosen college student, so the height you'd measure on a ruler, there's an infinite number of heights once you break down the decimals into smaller and smaller things. So the amount of electricity used to light a randomly chosen classroom, that's another thing where, again, you've got decimals, and so this, you can't list the number of things. We'll think of it as continuous. So in summary, think of discrete things as like counting problems or really small problems where you can list 4 or 5 outcomes or 10, whereas these you can't list them. So they're called continuous. Okay, so we have a probability distribution for a discrete random variable specifies the probability for each possible value of that variable. So this is a complicated looking definition. All this is saying is the distribution tells you the probabilities for each outcome. So I'm going to back up to this first slide I showed you. This is a probability distribution. This is an example of one. So a probability distribution, it lists the probabilities for all the outcomes. So you see the outcomes, you see the associated probability. So oftentimes we can represent probability distributions in tables like this. For a discrete random variable, we can list the outcomes, we can list the probabilities. These are the 2 properties of probability distributions, and I think we've seen both of them before. So the first property is all the probabilities, each one has to be between 0 and 1, or it could be 0 or 1, but they have to be between 0 and 1, including those 2 endpoints. For each possible value, the sum of the probabilities has to equal 1, and we've seen that before too. So for instance, if you look at my probability distribution here, all these probabilities are between 0 and 1. They're a little bit bigger than 1. They're a little bit bigger than 0, but they're all less than 1. And the total of the probabilities, if I were to add them all up, is exactly 1. You add up 1/6 to itself 6 times, you get 6 out of 6, or 1. So that's a true probability distribution. But these are the 2 conditions, and one thing we'll have to do is check distribution to make sure that it is or isn't a probability distribution. If it is, we can do stuff with it. If it isn't, we're just going to throw it out. So if you look at this probability distribution, you see it's discrete. You can list the outcomes. There's 4 of them, these numbers. And then you want to check the conditions. So the first one is make sure all the probabilities are between 0 and 1. And, oh, look, this one's not between 0 and 1. This one is less than 0. So this is not a probability distribution. Probability distribution. So we're going to not use this because this isn't a probability. So this whole thing is worthless. We're going to throw it out. If you look at this next one, we've got another discrete random variable. You see how there are 5 outcomes? You can list all 5 of them. And look, these are negative. That's okay. These x values can be negative. What can't be negative is these numbers, the probabilities. So it's okay if these are negative. But the issue with example 1 was one of these was negative. And the probabilities themselves, the stuff in this right column, has to be between 0 and 1 or 0 or 1. So this is discrete. There's 5 outcomes. There they are. And these are the 5 probabilities. And it looks like they're all between 0 and 1, which is good. So that's the first condition. The next condition is that they all have to add up to be 1. So let's go ahead and add up these probabilities. And if they add up to be 1, then we've got a probability distribution. So these numbers add up to be 12, 13, 14, 15, 20. They add up to be 20. Then I carry the 2. I got 2, 5, 6, 7, 8, 9, 10. So then I'll carry a 1. Oh, look, that's the only one. Oh, look, they add up to 1. So this is a probability distribution. It's not a hard thing to check if something is or is not a probability distribution. Just check and make sure these are all probabilities, which means they're between 0 and 1. And then add them all up and make sure they add up to 1. If they're off by even a little bit, you don't have a distribution. You can't use it. Here's another example. It's discrete. There's 4 outcomes. There they are. Oh, and look, one of these outcomes is bigger than 1. That one's bigger than 1. So this is not a probability distribution. See, it's pretty easy to check if something is or isn't a probability distribution. So I can't use this because these aren't true probabilities. They don't add up to 1. That's not a real probability. So I'm just going to throw that out and not use it for anything. So, like I said, it's pretty easy to check. Let's look at using probability distributions to compute probabilities. So I have a probability distribution here. You can check on your own and make sure that it is truly 1. Make sure these numbers add up to 1. But I'm going to use this and find some probabilities. This represents 4 patients that have made appointments to have their blood pressure checked at a clinic. Let X be the number of them that have high blood pressure. The probability of distribution of X is as follows. So this would mean that 0 of the 4 patients have high blood pressure. This would mean 1 of them has high blood pressure. This would mean 2 of them have high blood pressure. This would mean all 4 of them have high blood pressure. So that's what these numbers mean. These are the chances that they occur. We want to find the probability that either 2 of them or 3 of them, or both, remember that or means this one or that one or both of them. Find the probability that 2 or 3 or both has high blood pressure. Now, I guess it's kind of a silly thing because it's not possible for 2 and 3 to have both. It's either going to be 2 people exactly or 3 people exactly. So you can ignore the both part. These are mutually exclusive events. Mutually. This isn't working. Mutually exclusive. And that's just because the way we're listing it, it's either exactly 2 people or exactly 3 people. It can't be both. Like if it's 2, then it's not 3, and if it's 3, then it's not 2. So that means that the probability that 2 or 3 have high blood pressure is equal to the probability of 2 plus the probability that 3. And we won't subtract the both because they're mutually exclusive. So this is a simpler problem. So this is equal to 0.27. So I got that here. And this is equal to 0.08. I got that here. So the probability that 2 or 3 have high blood pressure is equal to 0.35. And that's as simple as that is. So that's really nice. So most of the time when we make a probability distribution, in fact, if we turn it into a table like this, I think the events have to be mutually exclusive, which means if we're doing one or another or several, I think we can just add up the individual ones and not worry about the and part because they're going to be mutually exclusive. So these probabilities aren't too hard to find. The probability that more than one of the patients has high blood pressure, we can rewrite that more than one. We can rewrite that into something that's a little more helpful. Like why don't we say the the probability that 2 of them have high blood pressure, or 3 of them, or 4 of them. And remember, these are mutually exclusive events, which means we can have 3 ors when they're mutually exclusive because there's no like and parts to subtract. And so this isn't actually that messy or complicated because they're mutually exclusive. This is just the probability of 2, something's not working, of 2 plus the probability of 3 plus the probability of 4. And I've already done some of those. So this is 0.27 plus 0.08 plus 0.09, I'm sorry, 0.01. This is equal to 0.36. So that's not bad. Not bad at all. The probability that more than one of them have high blood pressure is the probability of 2 or 3 or 4 of them. So either exactly 2 or exactly 3 or exactly 4. Add them up. They're mutually exclusive. So that breaks down to that. And nice. So it's really not hard to find probabilities once you have the distribution, which is nice. Let's do another one. Let's do the probability that at least one has it. Now you can see this could work just like the last one. At least one would mean 1, 2, 3, or 4. I'm going to do our little at least one trick because I think it's a great trick and I want to convince you it's a great trick. So our at least one trick says we can that the complement of at least one is none. So this means 1, 2, 3, or 4. This means 0. And usually it's easier to do the 1 minus none trick when you're doing an at least one problem. You could do it the long way and add up all 4 of these, but I'm going to do it the easier way and so do 1 minus 0.23. I'm sorry, that's a 2. 0.23, which is equal to 0.77. Right, so that's that. So again, you could add up all 4 of these numbers instead and get 0.77. My way is quicker and I like it and it's clean and it works. So remember, don't forget the at least one trick. Sometimes you have to do it. Sometimes it just makes your life easier. So once you have the distribution, it's not hard to find probabilities. This is an example where we don't have the distribution, but we do have some information that's going to help us find one. So what we have are 1,000 parking spaces. I'm going to go ahead and identify this as the total number of things we have. Of these, 142 are long-term parking that costs $2 per hour. 378 are short-term that costs $4.50 per hour. 423 are uncovered long-term. So I guess these are covered long-term. I missed that. Those are covered short-term. These are uncovered long-term that cost $1.50 per hour, and uncovered short-term that costs $4 per hour. A parking space is selected from this population as random. So we'll treat this as a population, and we're selecting something from the population as random. So I'm going to call that capital N. Let X represent the hourly parking fee for the randomly sampled space. Find the probability distribution of X. So X is going to represent the fee, and as you can see, we have 4 different fees. We've got 2, we've got $4.50, we've got $1.50, and we've got 4. And so I'm going to go ahead and list those in my table down here. I'm going to list these 4 X's, and I'll go from least to greatest because that's usually how this is done. So I've got $1.50, I've got $2, I've got $4, and I got $4.50. And then I want to find out the probability I randomly select one of these 1,000 parking spots and end up in one of these 4 categories. So the way I'm going to do that is I'm going to find the probability that I get the 150 spots, which probability is going to be the proportion or the number that are in this category, which is 423. So 423 of them are in this category. So it's going to be the number in the category over the whole sample size, in this case, the population size. So this is the chance that I randomly pick something in this category because there's 423 of them and I got 1,000 total. And this is equal to the number 0.423. Dividing by 1,000 is easy, just move the decimal to the left 3 places. So I got 0.423. And then I'll do this for the other ones too. So the probability that I randomly select a $2 space, well, I need to find out how many $2 spaces there are. There's 142 of them over 1,000. And I get 0.142. And then the probability that I randomly select a $4 space, well, I need to find out how many of them there are. There's 57. So it's going to be 57 over 1,000. Be careful with this one. You want to move the decimal to the left 3 spaces, so it'll be 0.057. And then the probability, I randomly select a $4.50 space. That's going to be the number of $4.50 spaces, 378 over, oh, that's an 8, over 1,000, which is 0.378. And that's my probability distribution. So what I did was I identified all my possible X values, which they were there in the problem, and they told me X is the phi. So I found the 4 phis. And then I found the probabilities associated with each one using the same methods we used in previous videos when we found probabilities. It was the number in the category over the total number. And so once I found each one, I just put them in the table and matched them up appropriately. And there's your probability distribution. So we saw problems where this was already made, and we can use this to find probabilities. But as you can see, when you have data like this from a population, you can compute all the probabilities and make your distribution yourself, and then use that for whatever you want. So once it's summarized in the table, you can do a lot of things with this table. So if you want to check our work and make sure that we did it right, all these numbers are between 0 and 1. You want to add them up, and we'll get the number 1. That's a good sign that we've done everything well. And that's how you make a probability distribution.